Hi all, in this video we are going to study what is magnetic scalar and vector potential. So in electric fields we studied electric potential and it is a scalar quantity. So now we are going to study what is magnetic scalar and vector potential. So in magnetic field we have scalar potential as well as vector potentials are there, but in electric field we studied electric potential, which is a scalar quantity. So now we can define what is magnetic scalar and vector potential. So the potential associated with magnetostatic field B, the magnetic potential could be scalar Vm or vector A. So the magnetic potential associated with magnetic field B is either scalar quantity, that is represented as Bm, or either vector quantity, that is A. To define Vm and A involves recalling two important identities. So to define what is Vm and what is A, we are using two relations, that is del cross del V equal to 0. That means curl of a gradient of a function is always 0. Similarly, we studied that gradient of divergence of curl of any vector is also 0. We are using these two relations to define this scalar potential and vector potential. So the potential associated with magnetic field is called as scalar potential Vm or vector potential A. Next, our aim is to define this potential. For that we are using two relations. One is curl of a gradient of a function is always 0, or divergent of curl of any vector is 0. Then we can say that in electric field we can say that E is equal to negative gradient of potential, or E is equal to minus del V. So we can define the magnetic scalar potential Vm as related to H as H is equal to minus del Vm if J equal to 0. So for a medium having J equal to 0, then only we can define magnetic scalar potential. So remember, for a medium, if it have J equal to 0, current density is equal to 0, then only we can define this scalar potential, magnetic scalar potential Vm, and that is related as H is equal to negative gradient of the scalar potential, negative del Vm. So that is the definition of this magnetic scalar potential. And we can combine equation 1 and Ampere's law. So our equation 1 is H is equal to minus del Vm, and the Ampere's law is del cross H is equal to J. So we can write this equation H as del cross minus del Vm. So del cross minus del Vm, as already we said that the curl of gradient of a vector is gradient of a function is always 0. So del cross minus del Vm is equal to 0. So the magnetic scalar potential, or we can say that, which is equal to J, so that we can say that J equal to 0. So the magnetic scalar potential Vm is only defined in a region where J equal to 0. So that's the definition of magnetic scalar potential. That means the potential associated with a magnetic field in a region where J equal to 0 is called as magnetic scalar potential. And also we satisfy this Laplace equation just as we does for electric field. So in case of electric field, we know that del square V equal to 0, and that is called Laplace equation. See here, similarly here also the magnetic scalar potential will satisfy this Laplace equation, del square Vm equal to 0, because J equal to in a region where J equal to 0. So in a region where J equal to 0, then only this Vm is defined. Then that time this Dm will satisfy the Laplace equation del square Vm equal to 0. So next we can see what is magnetic vector potential. So for a magnetic field, we said that according to Gauss law in magnetic field, the surface integral of B dot ds equal to 0. So we can say that according to this Gauss law, if we are taking the surface integral of any vector is the volume integral divergence of that vector, so you will get it as del dot B equal to 0, and this equation is called Maxwell's second equation, or Maxwell's equation in magnetic field. So we can say that for a magnetostatic field del dot B equal to 0. Static magnetic field, we can say del dot B equal to 0. To satisfy equation 4 and B simultaneously, we can define a vector magnetic potential A in Weber per meter. So in our second equation, del dot del cross A equal to 0. So to satisfy this equation and this del dot B equal to 0, that means del dot something is equal to 0. We know that del dot B equal to 0. So we need to find what is this B in terms of any other vector. So that is called B is equal to del cross A. So that means del dot del cross A is always 0. So this magnetic vector potential is nothing but B is equal to the relation to this field strength is that B is equal to del cross A. Or we can write this potential. We already defined that the potential is line integral of dq by 4 pi epsilon 0 r. Similarly, we can define this magnetic vector potential A as the line integral of mu 0 idl by 4 pi r for line current. So the magnetic vector potential, magnetic scalar potential is defined as H is equal to minus del Vm, and similarly this magnetic vector potential is defined as B is equal to del cross H, del cross A, or we can write A as line integral of mu 0 idl by 4 pi r for line current, and we can also say for mu 0 k ds by 4 pi r for surface current and mu 0 j dv by 4 pi r for volume current, where k is the surface current density and j is the volume current density, etc. So and then this is called magnetic vector potential. So we can also define this magnetic flux as psi is equal to, we know that the magnetic flux is the surface integral of B dot ds. Here the surface integral of B is changed as del cross A ds. Or we can say that we know that according to Stokes theorem, the curl of any vector is the line integral, surface integral of curl of any vector is the line integral of that vector. So we can say that the flux related to this magnetic vector potential as flux is equal to line integral of A dot dl. And in case of scalar magnetic potential, we already said that it will satisfy Laplace equation. Similarly, the vector potential will satisfy the Poisson's equation. So this according to this Poisson's equation, we can write it as del square A equal to minus mu 0 j. So for that we are taking a vector identity, that is del cross A is equal to back cap rule, back minus cap rule you can apply. So you will get del cross A is equal to, consider first del as A, second del as B and A as C. Then you apply back minus cap rule. Then you will get it as del into del dot A minus del square A. Then square A. Then we can replace del cross A as B, because our relation is B is equal to del cross A. So you will get del cross B is equal to del into del dot A minus del square A. In that del dot A is 0. We are selecting del dot A equal to 0. So you will get del cross B equal to minus del square A, or in that B are replaced as mu 0 H. So you will get mu 0 is a constant, so we can take it outside. So you will get mu 0 into del cross H is equal to minus del square A, or del square A equal to minus mu 0 del cross H, where del cross H is equal to J due to Ampere's law. So you will get del square A equal to minus mu 0 J. And for electric potential, we know that the Poisson equation is del square V equal to minus rho V by epsilon. So that's the Poisson equation in electric potential. So for electric potential, it is a scalar quantity only, and it will satisfy both the Laplace equation as well as Poisson's equation. And for the Laplace equation is defined for charge free medium in that case. But for magnetic vector potential, it consists of scalar quantity as well as vector quantity, and the scalar quantity will satisfy Laplace equation and the vector quantity will satisfy Poisson's equation. And the scalar quantity is represented as, scalar magnetic potential is represented as H is equal to minus del Vm, where Vm is the scalar magnetic potential, and the vector magnetic potential is defined as B is equal to del cross A, where A is the magnetic vector potential. We can also derive the Ampere's law using this vector magnetic potential A. So for that we are taking the line integral of H dot dl expression. So according to Stokes theorem, the line integral of any vector is the surface integral of curl of that vector. So we can replace this as surface integral of del cross H ds. Then the relation between H and B is H is equal to B by mu 0. So we can replace H as B by mu 0. So with respect to surface, this mu 0 is constant. So we can take it outside. So the remaining equation is 1 by mu 0 into surface integral of del cross B. But B is, we studied that B is, what is B? B is del cross A. So we can replace the equation B is as del cross A. So you will get the 1 by mu 0 surface integral of del cross A equal del cross A ds. So that is the line integral of H dot dl. Then we already studied that del cross as we found it is del cross A is minus del square A, and it is minus mu 0 j. So it is minus del square A, so it is mu 0 j. Then we can rewrite our equation as line integral of H dot dl equal to 1 by mu 0 times this surface integral of del cross A ds. In that the del cross A ds become mu 0 j. So that equation become line integral of H dot dl becomes 1 by mu 0 into surface integral of mu 0 j dot ds. So mu 0 cancel. So the line integral of H dot dl becomes surface integral of j dot ds. That surface integral of j dot ds is nothing but current itself. So already we studied that according to Ampere's law, the line integral of H dot dl is known as current itself. So this way we can derive this Ampere's law using this magnetic vector potential. So that's all about our magnetic vector potential and the magnetic scalar potential.